Building Construction for the Fire Service, Week 6, Homework Problem 3, Part 2. So in the first video, we were able to arrive at the conclusion that the force in the y direction provided by member DH was 10,000 pounds. It was a 10,000 pound upward thrust on point D, and the compression in component DH was 14,140 pounds. And actually, we were able to also determine that the force in the x direction provided by DH was negative 10,000 pounds. Remember, it's negative because it's a leftward push. And so now we've figured out the compression in DH, and we've figured out our basic reactions at point A and G, but we still need to figure out the forces in DE and IH. And to get any further with this, we need to look at moments about point A again. So if I think about the moments about point A, let's write down what we know. So the sum of the moments about point A equal what? Well, this 10,000 pound load is directly in line. It doesn't generate a moment because it's the effective length of the lever arm is 0. But I've got 15,000 times 8, which is 120,000. And in this case, it's going to be a negative number because it's a negative 15,000, but we're 8 feet to the right, so a negative times a positive is a negative. So 120,000 pound-feet, producing a clockwise rotation, plus I have a 20,000 pound load at a radius of 16 feet, so that's 320,000 pound-feet. And that's it for loads on the structure that are creating moments about point A, because remember, we've forgotten about everything to the right of the squiggly line here. That's it, I should say, for the loads that are given in the diagram. Now let's think about other forces that are being generated. We have this 10,000 pound upward thrust at a distance of 16 feet. So that is going to be a positive moment because it's going to produce a counterclockwise rotation. So 10,000 times 16 is a 160,000 positive pound-foot moment. Additionally, we have the horizontal component of the thrust of member DH, which is acting on an effective lever arm of 8 feet. So it's 10,000 pounds leftward on an 8-foot lever arm, which is going to give us 80,000 pound-feet. So here we have the formula written out. These are all the moments we've accounted for so far. The last ones we need to account for are moments created by forces in component IH and moments created by forces in component DE. But if I look at component IH, it's directly in line with pivot A, which means that its effective length of the lever arm is 0. It can't generate a moment. Component DE can generate a moment, and the moment it's going to generate is the length of the lever arm, which is 8 feet, times the force in DE horizontally, which we've already determined to be 10,000 pounds. So plus 8 times 10,000 pounds. I'm sorry, 8. We've not yet determined the force in DE, so it's 8 times the force in the x direction in component DE. And all of these moments need to sum to 0. So if I push this thing around a little bit, I end up with the sum of all of these moments, which is 200,000. Okay, and I guess specifically it's negative 200,000. So I end up with negative 200,000 plus 8 times the force in the x direction of DE equals 0. Or another way I can think of this is 8 times the force in the x direction exerted by DE equals 200,000, because now I've moved it over onto the right side of the equal sign. So now I just do division, and I find that the force that is exerted by the component DE is 200,000 divided by 8, which is 25,000 pounds. Now, I got to be a little bit careful with sign convention here. The question becomes, is this pulling to the right, or is this pushing to the left to create the moment I need? And it's clear, looking at the diagram, that it's pushing to the left, which tells me that component DE is in 25,000 pounds of compression. Now, the last step is to look at the sum of all of the forces in the x direction and figure out the forces in IH. So final step, we're going to take a look at the forces, all of the forces in the x direction. So sum of forces for the whole system, or for the whole segment we're looking at, in the x direction. So what do we have? Well, we've got, we know that DH is pulling to the left, or pushing to the left with 10,000 pounds force. We know that DE, because it's in compression, is pushing to the left. In this case, with negative, we would think of it as negative 25,000 pounds force, right, because it's a leftward push, plus the force that's developed in the x direction in component IH. And all of these have to add to 0. So if I think about component IH has got to be developing a rightward pull of 35,000 pounds on point I. So the quantity is 35,000. Now, the question is that tension or compression? Well, if I'm pulling point I to the right here, clearly that has to be tension. So through all of that analysis, we were able to develop the forces in these three members, this IH here, this DH, and this DE. We were able to figure out reactions at the bases, and we could basically just continue this process for every component in this truss and identify forces in each and every one of these things. It's a bit tedious, but it's a powerful process, because if you go through this, or if we were to automate this on the computer, we can make really good predictions about how this truss is going to fail under fire conditions.